All right, we're going to get into looking more specifically at solutions measuring solute concentrations now. So let's kind of jump into it. First off, the relative amount of solute particles is what we refer to as concentration of a solution. Okay, so just bear in mind, if my solute, let's say I have a 10% salt solution in water, right? So what this tells us is that the amount of salt compared to the total solution, it's 10% salt in a complete 100% solution. All right, so the way that we can express that, there are several different scales. The first one that I just represented here, this is percent by mass, and it's very common. The way that we find percent by mass, it's a function of this formula. The percent mass is equal to the solute mass, okay, so the thing that goes in, divided by the solution mass. And then because it needs to be a percentage, we then take that decimal that comes out of this and multiply it by 100. Now, one very important thing to note here is that it's the solute divided by the total solution mass, okay? So our total solution mass is going to be solution equals the mass of my solute added to the mass of the solvent. Okay, so keep that in mind. This is going to have to go into the bottom in my denominator here. Next, another common scale is parts per million. And parts per million it's related in that it's a mass-based scale to this percent mass, but it's a slightly different variation. This is used heavily in industry. Parts per million can be found with this formula. You take the solute mass, and it must be in milligrams. Okay, so you're going to have to convert that using King Henry or dimensional analysis. So we take our solute mass, and this time around, we want to compare this not to the total solution mass, but to the solvent mass. And the solvent mass must be in kilograms. So that's where our million comes in. There are 1 million milligrams per kilogram. So the units automatically are going to relate these in terms of parts in a million. Next, you can express concentration as grams per liter. So this time around, instead of comparing just mass, we're looking at mass as well as volume. And per means divided by. So the number of grams divided by 1 liter. So this concentration can be determined very specifically if we're talking about a water-based solution. So a water-based solution, we need to understand that density is going to relate mass and volume, because density is the mass divided by the volume for some solvent or any liquid substance or solid or gas. So density is mass over volume. If I'm discussing a water-based solution or water in general, I typically am just going to use the density of water. Okay, so the mass of my solvent is going to be used to convert into the volume of the solution. Okay, we typically in most solutions we're going to find that the added volume that we get from the solute mass is going to be fairly negligible. So we assume mass, let's say if I had a 500 gram water sample, I can convert that using the density of water. 1 gram is equal to 1 milliliter of water. So I know that 500 grams would be equivalent to 500 milliliters. So knowing this, I can then find liters based off of that, and we can determine grams. And we'll do that in a second. But let's get on to our last concentration scale. Our last scale is molarity. Okay, so molarity it's related to grams per liter. Instead, though, we're looking at actually counted units, not mass, but the counted number of molecules or moles per liter. So molarity is going to be expressed with a capital M. So if I have a solution that is, let's say 3.50 moles per liter, instead of writing as 3.50 moles per liter, I will write out it is a 3.50 molar, with a capital M to indicate that, solution of whatever the solute is. But in order to find it, what we're going to do is we're going to say that molarity is equal to the number of moles of solute divided by liters of solute. Okay, so you can take a number of moles and a number of liters, divide across, and that will give you your molarity value. Now, to give you a better example of this, I want to make sure you understand we can use dimensional analysis to convert between concentration scales. So I'm going to give you a, for instance here, 60 grams of carbon monoxide is dissolved in, I will say, 500 grams of water, H2O. So 60 grams in 500 grams. The thing that we can, I guess, first sort of break down is, let's say I'm trying to determine the percent mass of this solution. What I would need for that percent mass is to know the solute, the solvent, and the solution's mass. So 60 grams of CO, this is my my solute mass, okay, because it goes into this. Another indicator that we can use is this is a smaller amount. So this is the solute mass. This here is the solvent mass. And if I combine these two, I see that 560 grams is going to be the solution mass. So to find percent mass, we recall it is the mass of solute divided by the mass of solution times 100. So what we can do with that is we can say it'll be 60 grams, the solute, divided by 560 grams, the solution's mass, and multiply by 100. So I'll pull out my trusty calculator. We're looking at 60 divided by 560. So 60 divide 560, and then multiply that by 100, and verify that the format, yeah, that is correct. We get 10.71%. So coming back here, so this is equal to a 10.71% solution. That's unrounded, but I'm going to leave that as it is for now. Now, if I want to convert between these concentration scales, let's say I didn't want percent mass, but instead I want parts per million. Recall that parts per million, ppm, was equal to the solute in milligrams divided by the solvent in kilograms. So I can take the solute, 60 grams, convert that 60 grams into, it is 60,000 milligrams. Take our solvent mass, 500 grams, and convert that into kilograms, which would be 0.5 kilograms. And then we can do the math on that, 60,000 divided by 0.5. And that is going to be 120,000 ppm. Now, typically when we're dealing with ppm, we're looking at concentrations that are much, much less than 10%. So this ppm number isn't nearly as big. But hopefully you have an example of how that should look now. Next, what we're going to do is we're going to look at the number of grams per liter. So again, recall we have 60 grams of CO as my solute mass, but we need to figure out how many liters we have in 500 grams. So what we'll do is recall that 500 grams of water, we can use the density of water to get grams into milliliters of water. 1 gram per mil means I have 500 milliliters of water. If I wanted to know the number of grams per liter, though, these milliliters need to be converted. So what I'll do is I'll say 500 milliliters. We can convert using dimensional analysis, but I know that that's a shift of the decimal 3 places to the left, so that would be 0.500 liters. Now I can use this to do my conversion. So we'll take our 60 grams of the solute, divide that 60 grams by 0.500 liters. What that's going to come to is 120 grams per liter of this solution. Now, the last thing that we're going to focus on is our molarity, the number of moles per liter. And what we'll need to do here now is I have 60 grams and 0.500 liters. What I can do is I can convert grams using molar mass. And we're looking at carbon monoxide. So if we look on the table, we see carbon is 12, oxygen is 16. So what we're going to have here, 12 plus 16 gives 28. So 60 grams, there are 28 grams in 1 mole for our carbon monoxide. So 60 divide 28 gives us 2.14 moles. So I'll take that 2.14 moles, and now I can divide it by the number of liters that I saw before, 0.500 liters divided by 0.500 liters, and we will get 4.28 as the molarity. It is a 4.28 molar carbon monoxide solution. So hopefully you saw how we can use this one sample and we can express it in multiple ways. The one key that you need to remember is that density relates mass and volume of a solution. So the solvent mass in a water-based solution can be converted directly into the solution volume. Alright, so I'm going to give you some time to work these practice problems. I'm actually going to pause the video here and then resume it, just because I know this is taking a little bit of time. Maybe you need to digest that a bit, and then I will work these out in just a sec here.